Let us start this lecture with a thought process that nature doesn't like hardness in speech. So, there is no bone in tongue. It is important to have that in our mind, and let us recall what we learned in the last lecture. In the last lecture, we basically discussed about how to estimate the adiabatic temperature, and then we move into how to calculate the equilibrium composition of a mixture. Keep in mind that it is important to find out equilibrium composition for estimation of the adiabatic temperature, and so also for estimation of chemical composition at equilibrium we need to calculate the adiabatic, we need to have the temperature also. So, therefore, both are interlinked and it is being done in a iterative manner by minimization of Gibbs free energy and also Helmholtz free energy, and there are several softwares which are available, which I did not mention in the last lecture. One of them SP273, this is basically was being made by the NASA, this is hence it is known as the NASA 273, and another is gas equations, which is available freely in internet. You can use that for calculating the equilibrium composition, adiabatic temperature, and also certain properties like gamma and Cp, Cv values, all those things which are required very much for calculating the various parameters in rocket engines and also other combustion systems. Today we will be discussing about how to analyze a rocket engine considering the ideal conditions. Why we will be considering ideal? Because of fact that if you look at rocket engine, the process is very complex in nature, whether you use a solid propellant rocket engine or you use as a liquid propellant rocket engine, the flow processes which will be very much quite complex. If you look at the flow here, the lot of combustion will be taking place and this flow will be moving little slow velocity. After that it is basically maybe recirculated here and then move into this flow, and it is three-dimensional in nature. The flow will be three-dimensional in nature, and velocity what we will be considering, and the flow is turbulent inherently, and to some extent it is unsteady, and lot of interaction will be taking place in this rocket engine. This is a solid propellant rocket engine, SPRE. So, and that is true also for the liquid propellant rocket engine, and that is true also for the hybrid propellant rocket engine. The flow processes are quite complex, and what we need to have here is that we will be making some assumption. Keep in mind that this rocket engine is having two components. One is your thrust chamber and other is your nozzle. So, if you look at this, I call it as a basically thrust chamber. This is thrust chamber, and this already I have told it is a nozzle. That together thrust chamber plus the nozzle is known as a rocket engine. And as the flow process is quite complex, so therefore it is difficult to analyze it, and we will be making some assumptions, and let us see what are those assumptions. So, what we are assuming, steady one dimensional flow. If you look at the flow in this case is basically, if I take this as a x direction, right, and this is your r direction, right, this is your x direction, and there will be also theta direction here, three-dimensional. So, the flow is really three-dimensional nature, but however we are considering flow not only to be steady, but one-dimensional and inviscid flow, and there will be also boundary layer which will be occurring here, and this is boundary layer, and however, as the boundary layer will be small and then the flow will be particularly in the nozzle, right, flow will be very high velocity, it is accelerating one, the boundary layer will be small. So, therefore, we can consider the flow should be inviscid in nature, and details of combustions are being ignored because of fact that it is quite complex. There is the solid phase combustion and then also the two phase combustions and gaseous combustion, all this going on, and it is quite involved and several chemical species will be involved in this. So, therefore, we are assuming as if the heat being released, that is all we will be considering due to the combustion of fuel and oxidizer in the propellant. And working fluid is homogeneous in nature, but actually it is always heterogeneous in nature. You consider any kind of rocket engine, whether it is a solid propellant rocket engine or liquid propellant rocket engine or a hybrid. The amount of mass due to the condensed phase, solid or liquid phase, is negligibly small as compared to the gaseous fluid. Therefore, we will be considering it to be gas. That is the reason what we are taking. And ideal gas law with constant specific properties can be considered for this analysis. As I told earlier, we can assume the gas to be ideal, as the temperature here it will be order of something 3000 Kelvin, and pressure is moderate, not very high, so that the ideal gas law will be violated. And we will be using constant specific heat for the analysis of the rocket engine, but keep in mind that it cannot really remain constant because the temperature will be changing all the time. If I go along with the rocket thrust chamber and also the nozzle where the expansion will be taking place, there will be change in the temperature along with the direction of the nozzle towards its exit. So, therefore, that is an assumption we will be making for simplicity, and no heat transfer will be taking place from the rocket engine, but actually there will be some heat transfer, at least in solid propellant a lot of heat losses will be there from the nozzle and also in other parts. So, that is not true, and we are assuming it to be, it should be 0 or adiabatic, but that is not true in real situations. And flow is isentropic except across the shock wave, but that is also not true because of various reasons, like there is a boundary layer, there will be mixing, there will be interactions and heat losses. So, therefore, it cannot be isentropic, but however, we are considering to be isentropic. And uniform chamber conditions at the nozzle entrance. The nozzle entrance here, if you look at, this is your nozzle and entrance here, that flow need not to be uniform. This may be some parabolic profile you can think of using that, because there will be boundary layer growth in this on the solid surface. But however, what we are assuming, the real one and ideal one, what we will be assuming is as a uniform velocity at the nozzle entrance and also at the exit. Here, if you look at this, the two dimensional flow, there will be a axial component, there will be a radial component of velocity, but we are considering the flow should be uniform over in this region. At the exit of this flow, at this point I am just drawing here, that is a uniform flow. That is the things what we will be assuming. And the flow properties, namely pressure, temperature, density, remain constant at the nozzle entrance. At this here, all these properties will be remaining constant, but that is not true. Particularly velocity, temperature, all will be changing along with the radial direction, so also in theta direction. Velocity at the nozzle entrance is negligibly small. Here the velocity will be very small, like if you look at this x will be is basically very small in nature, maybe few meter per second. And as compared to exit, exit will be very high velocity. This is your V e, exit velocity at this point. If I consider exit here, this is your exit. So therefore, this V e is at that point. And the gas composition across the nozzle remains constant, but that is not true. It will be changing, and we assume the flow to be frozen at the inlet to this nozzle. And these are the assumptions we are making, and the gas leaves the nozzle exit along the axial direction. As I told, this is along the axis. So therefore, we call it a axial direction only, and there is no radial component of the velocity at the exit of the nozzle, which is not true. But however, we will be assuming it to be uniform and along the axial direction only for simplicity. Now, let us use these assumptions for deriving a relation for the thrust equation of the rocket engine. In this case, we will be relating the thrust experienced by the rocket engine due to the change of momentum and also the pressure, that we will be doing that. And let us consider the rocket engine, which is having a control volume here. This is your control volume, right, and it is x direction, and this I can say is basically the y direction, or I can tell it as basically r direction. That will be better. So if you look at r will be better, and there will be a combustion will be taking place. This is your combustion chamber, where heat release will be occurring in this region, and this is your basically control volume, and this is control surface, and this is your control volume, right, control volume, which will be including the nozzle portion, and both the thrust chamber and the nozzle portion is, we call it as a control volume. And the hot gas, after being expanded in the nozzle, right, it is leaving the nozzle exit at a velocity V e, and which is having a cross sectional area. So this is your cross sectional area, which is A e, and keep in mind this is the exit velocity of M e, Mach number M e, that is exit. And keep in mind that this is the thrust which is experienced by the rocket engine when there is a change in the momentum of the fluid at the exit of the nozzle, right. To find out a relation for the thrust which is opposite to the momentum change, right, and that is can be derived by considering the momentum equation. And the integral form of momentum equation is this term, that is the rho v x dv integral over the control volume and rate of change of momentum per unit time. And this is your momentum flux, across this control volume, and this is your area, control surface area, and which is equal to the summation of forces acting on the x direction, and we are only considering the x direction, the rate of change of momentum. And keep in mind, for steady flow, this term, for steady flow, this term will be 0. Therefore, this term becomes 0 in the steady flow. And if you look at the momentum fluxes is the second term, that is basically is the integral of, this is the V x is the velocity along the x direction, and rho V x is the density, this is your density, and V x is the velocity along x direction. and this is equal to, for this, because only through the exit of the nozzle the gas is going out with the velocity v e. Keep in mind, along the x direction we are considering in this case, and then x, as we have already assumed the velocity to be uniform. This is a uniform velocity profile. So, therefore, it will remain constant, and V x, and then this is your basically mass. When you integrate it, you will get basically mass flow rate, and the V x is uniform. So, therefore, it is becoming basically the m dot into V e, because we are assuming the density to be uniform across this cross sectional area, and so also the density and also the V e, that is at the exit of this nozzle. So, therefore, the momentum flux term is nothing but m dot V e, and the pressure forces acting on this control volume will be basically that is summation of this force, and this is due to what? This is due to, if you look at control volume, there will be pressure which will be acting over every places inside, everywhere it will be acting, but also the other side there will be pressure P A, atmospheric pressure. So, keep in mind, this is small one, and this is a metal which will be balanced by the things, and it will be balanced all the time. And similarly, everywhere it will be acting P A, depending on what altitude you are having. And inside also the pressure will be acting, it may be changing as this getting expanded, right, becoming a smaller one as it the pressure, and this will be leaving at a pressure which is having V P E, P E. So, if you look at this, P will be balanced, is acting over here, P E, because it is moving. So, this will be just opposite to that. So, P E, and then there is also a pressure which will be acting just opposite to this P E, because if you look at, if you take a free body diagram and say that it will be balanced, there is also P A will be acting at the exit, and so also other side, all the sides of this rocket engine, and there is a force which will be acting on that side. So, therefore, the total force will be equal to the P A A E, which will be acting, and minus the exit pressure into A E, area, and the same area which will be acting, right. This is the area what I had, cross sectional area, at exit, and this is your thrust, which is opposite reaction to this momentum. So, therefore, if when I substitute over here in this equation itself, in equation 1, I will get F is equal to m dot E V E plus P E minus P A into A E, and this is nothing but your thrust. Keep in mind that this is a very important expression for thrust that you should keep in mind. Unlike in the aircraft engine or air breathing engine, there is no term which is due to the incoming fluid. There is no negative term in the momentum equation. This is basically momentum. thrust, and this thrust is due to the pressure thrust. There will be pressure change in that. So, as a result, you can see that the thrust is independent of the flight velocity, because the flight velocity is not coming in this expression, and sometimes of course, like we need to look at which term is important, and then as the altitude is changing, this P A will be changing along altitude. So, therefore, this pressure term will be also varying. Sometimes we need to express this thrust, total thrust, that is contributed by the momentum and the pressure in terms of momentum thrust, for which we will have to define the equivalent exhaust velocity, that is V E Q is nothing but a F into m dot, or the mass flow rate at the total mass flow rate through the engine, is equal to, if I do that, this thing here, this will be V E plus P E minus P A divided by m dot into A E, and this is, keep in mind that very important, because whenever we will be looking at some terms, we can look at in terms of that. This is total mass flow rate of propellant. Now, we will have to look at the thrust equation little bit further and see that how it can be considered. And as I told earlier, that the pressure which will be acting all the places here in the nozzles, and this is your atmospheric pressure, this is your atmospheric pressure, and the thrust is opposite to the direction of the momentum of the propellants, is just opposite to that. Keep in mind that we have derived this thrust expression, and in the space region, if you look at the deep space, this P A will be 0. This will be for space region, this P A will be equal to 0, and keep in mind that this P E will be changing depending upon the extent of expansion what is taking place, and therefore, this term may be if P is greater than P A, then naturally this pressure term P E minus P A E will be greater than 0. That means, it will be positive, right, greater than 0. If P E is greater than P A, that means it is basically positive. And if P E is less than P A, naturally what will happen, P E minus P A E, this term will become less than 0 or negative. Negative means that will be really taking something from this, the momentum flux. As a result, that thrust will be lowered down for the same kind of V E and mass flow rate of propellant. So, therefore, it is very important and to see that under what condition this maximum thrust one can get, because keep in mind that when this is expansion P is taking place, the extent of expansion will be dependent on also the momentum flux what is changing, because how much expansion is taking place, as that V E will be changing. V E will be dependent on the extent of exit pressure, both are related. So, therefore, it is very important to look at like which term is playing an important role and under what condition it can be maximum. Keep in mind that this maximum thrust can only take place when it is nozzle is fully expanded, that is P E is equal to P A, and thus the maximum thrust is obtained as m max is equal to m dot P into V E. So, this is a very important expression you should keep in mind, that is also you can obtain by differentiating this equation and with respect to P A, and then you can really make it derive this expression, and I leave that as to for you to look at it, and keep in mind that this thrust expression is very important and which we will be using and for our analysis. So, how does the thrust vary with altitude? As I told that PA will be changing, PA varies with altitude. So, therefore, as the PA is varying for a same area ratio of nozzle and also same range of pressure, so you will find P will be, let us say, if it is remaining constant, which is not true, but still there will be change in the thrust expression. So, the thrust, if you look at altitude, it goes on increasing, but after certain altitude it remains almost constant, and so also the specific impulse, and we are going to define the specific impulse, and keep in mind that the thrust is varies from 105 kilonewton to 128 kilonewtons for in this example, and so also the ISP is varies from 275 second to 310 seconds. With this I will stop over here, and then we will discuss more in the next lecture. Thank you very much.